On a Tuesday afternoon in March 2023, something appeared in our detectors that ripped a hole through everything we thought we knew about physics. A single particle, one subatomic messenger traveling alone through the cosmos. It arrived carrying energy that shouldn't be possible. Energy so extreme that when the scientists first saw the data, they thought their instruments had malfunctioned. They checked the calibration, they ran diagnostics, they looked for glitches, interference, cosmic rays, anything that could explain what they were seeing. But the signal was clean, the particle was real. And it was screaming, this wasn't just unusual, it was physically impossible according to every model we have. No star explosion generates this kind of power, no colliding galaxy, no supermassive black hole feeding frenzy, nothing in our catalog of cosmic violence comes close. The energy packed into this single particle was equivalent to a baseball traveling at 98% the speed of light, except this wasn't a baseball, it was smaller than an atom, 100,000 times more energetic than anything humanity has ever created in our most powerful machines. The Large Hadron Collider, the crown jewel of particle physics, can't even dream of reaching these numbers. And yet here it was, casually drifting through the Mediterranean Sea, slamming into a detector array buried under a mile of water. When the initial shock wore off, the real work began. Where did it come from? The team traced its trajectory backward through space, rewinding its path like a forensic detective following a bullet. They expected to find a smoking gun, a quasar maybe, a gamma-ray burst, some titanic cosmic event that could justify this level of energy. What they found instead was nothing, just empty space, a quiet, unremarkable patch of sky with no obvious source, no light, no radiation, no heat signature, nothing that screamed, "I just launched the most powerful particle ever detected." That's when the whispers started in the physics community. That's when researchers began dusting off old papers, forgotten theories, predictions made decades ago that were elegant, mathematically beautiful, but never observed in reality. And one name kept coming up: Hawking, Stephen Hawking, because buried in his equations from 1974 was a prediction that black holes don't live forever. They evaporate, they die, and in their final moments they don't fade quietly, they explode. If you're enjoying this deep dive into one of the strangest mysteries in modern science, do me a favor, hit that like button right now. It tells the algorithm that stories like this matter, that you want more investigations into the impossible, and if you're new here, subscribe. Because what we're about to uncover gets even stranger. Let's talk about what we think we know about black holes. The textbook version says they're cosmic vacuums. Gravity so intense that spacetime itself collapses into a point of no return called the event horizon. Cross that line and you're erased from the universe. You don't come back, you don't send postcards, you're gone. Forever. Black holes, in the classical sense, are eternal prisons. They grow, they consume. But they never die. Einstein's equations allow them to exist indefinitely, sitting in the void like scars on reality that never heal. But Hawking saw something Einstein missed. He looked at the edge of a black hole through the lens of quantum mechanics, and he realized the vacuum of space isn't empty. It's boiling with virtual particles. Matter and antimatter pairs constantly popping into existence and annihilating each other in fractions of a second. Normally, this happens everywhere in the universe with no consequences. But right at the event horizon, something extraordinary occurs. One particle from the pair falls into the black hole, the other escapes. And because that escaping particle is now real, it has to steal a tiny bit of energy from the black hole to exist. This is Hawking radiation, and it means black holes are bleeding, slowly, imperceptibly. A black hole the mass of our sun would take longer than the entire age of the universe to evaporate this way, trillions upon trillions of years. So for all practical purposes, we assumed we'd never witness it. It was theoretical, beautiful math. But not something you could observe in a human lifetime or even in the lifetime of civilizations. Except Hawking's equations revealed something else, something most people overlook. The smaller the black hole, the faster it radiates, the hotter it burns. A massive black hole is cold, nearly motionless in its evaporation. But a tiny black hole, one the size of a mountain compressed into the space of a proton, radiates furiously, and right at the end, when it's down to its last moments, it doesn't fade, it detonates. This is the Hawking burst, a final flash of energy as the black hole releases everything it has left in a split second. For 50 years, this remained a ghost in the equations, a theoretical endgame no one had ever seen, until that particle hit our detector in 2023. Here's what the researchers at the University of Massachusetts Amherst are proposing. They believe that particle, that impossible high-energy neutrino, was shrapnel, the dying scream of a black hole that's been floating through space since the universe was less than 1 second old. Not a black hole born from a collapsed star. Those are recent, those are huge. This was something far older and far stranger, a primordial black hole. In the first fraction of a second after the Big Bang, the universe wasn't smooth, it was chaos. A seething soup of energy expanding faster than the speed of light, but there were lumps, tiny fluctuations in density. Some regions were slightly more packed than others, and in those regions, under unimaginable pressure, gravity won. Matter collapsed before stars even existed, before galaxies, before atoms. These pockets of density crushed themselves into black holes on the spot. These primordial black holes could be any size. Some might be massive, but many, perhaps most, would be microscopic, the mass of an asteroid squeezed into a space smaller than a grain of sand. And here's the critical detail. If you do the math, if you calculate how long it takes a black hole of a certain size to fully evaporate through Hawking radiation, you find something eerie. A primordial black hole born with roughly the mass of a large mountain would take exactly 13.8 billion years to die. That's the age of the universe, right now, today. Which means we're living in the exact era when the first generation of these ancient monsters is reaching the end of their countdown. They've been ticking silently through the dark for the entire history of the cosmos, and now, all over the universe, they're going off. But there's a problem. Even an exploding primordial black hole following standard Hawking radiation shouldn't produce a neutrino with that much energy. The equations don't support it. Hawking radiation is smooth, thermal. It doesn't create sudden spikes of ultra-high energy particles. So if this was a primordial black hole, something else had to be involved, something we haven't seen before. That's where the dark charge comes in, and this is where the story goes from incredible to reality-shattering. The UMass team didn't just propose a primordial black hole. They proposed a charged one, not electrically charged, but carrying a load from a hidden sector of physics, the dark sector. We know dark matter exists. It makes up 85% of the matter in the universe. We see its gravity holding galaxies together, bending light, shaping the cosmic web. But we've never detected a dark matter particle. We don't know what it is. The UMass researchers are suggesting that primordial black holes absorbed dark charge in the first moments of the universe, and that charge changes everything. Imagine a black hole trying to collapse under its own gravity. Now imagine it's also carrying a charge that pushes outward, resisting that collapse. Gravity pulls in, charge pushes out. As the black hole evaporates and loses mass, gravity weakens, but the charge doesn't, it stays constant. Eventually, the two forces balance. The black hole reaches what's called a quasi-extremal state. It's a loaded spring. It's on the edge of catastrophic failure, and when it finally goes, it doesn't leak. It explodes violently, shedding that dark charge in a directional burst of ultra-high energy particles. This explains the neutrino. It explains the energy. And here's the kicker, it explains why only one detector saw it. Because if the explosion is directional, like a spotlight instead of a light bulb, then depending on where you are in the universe, you either see it or you don't. KM3NT in the Mediterranean was in the beam. Ice Cube in Antarctica wasn't. If you're still with me, drop a comment right now. Tell me what you think. Is this the most elegant solution you've ever heard, or does it sound too convenient? I read every comment. Some of you have theories that belong in academic journals. Let's talk about this. Now let's zoom out and see what this means for reality itself. If this detection is confirmed, if this really was a dark-charged primordial black hole exploding, we've just solved three of the biggest mysteries in physics simultaneously with one observation. First, dark matter. We've been searching for it for decades. Massive underground detectors, particle accelerators, space telescopes. We've found nothing. No WIMP particles, no axions, no exotic matter. But if primordial black holes are real and if they're scattered throughout the universe in massive numbers, they are the dark matter. We don't need new particles. We just need lots of tiny, invisible, ancient black holes, each one carrying mass. Each one pulling on galaxies, each one undetectable until it explodes. The ghost matter we've been hunting isn't a particle at all. It's a graveyard of black holes from the beginning of time. Second, the Big Bang. We can't see the first 380,000 years of the universe. The cosmos was opaque, light couldn't travel, we're blind to the actual moment of creation, but these black holes are fossils, they were forged in that first second. Their properties, their charge, their mass distribution, all of it encodes information about the conditions of the infant universe. Studying them is like reading a message in a bottle thrown from the Big Bang itself. This one explosion just gave us a direct probe into physics we thought was forever hidden. Third, and this is the big one, quantum gravity. For a century, physicists have been trying to unite Einstein's general relativity with quantum mechanics. Gravity works on the scale of planets and stars. Quantum mechanics works on the scale of atoms and particles, but they don't play nicely together. At the center of a black hole where gravity is infinite and space is quantum, the math breaks down. We get infinities, nonsense, paradoxes. But if black holes explode, if they don't collapse into a point of infinite density but instead bounce back in a quantum recoil, then the singularity doesn't exist. There's no infinite point. There's a minimum size, a quantum floor. This aligns perfectly with loop quantum gravity, one of the leading theories trying to unify physics. It says spacetime isn't smooth. It's made of discrete loops like pixels. You can't compress it infinitely. At some point it resists. The black hole can't shrink anymore. Pressure builds, and it explodes. This detection might be the first experimental evidence that spacetime is quantized, that gravity and quantum mechanics do merge, that we're not stuck with two incompatible theories. We're seeing the unification happen in real time in the sky. One particle, one impossible detection, and it's the key to everything. Here's what happens next. The team says we should see another one of these explosions within the next decade. Maybe sooner. Our detectors are already sensitive enough. We just have to be patient. If a second event matches the profile, same energy range, same directional pattern, we're not dealing with a fluke. We're dealing with a new class of cosmic phenomena. A population of primordial black holes that have been hiding in plain sight for the entire history of the universe, and they're starting to go off like firecrackers. Imagine that. The space between stars isn't empty. It's filled with these tiny ticking bombs, most of them silent, invisible. But every so often, one reaches zero on its countdown, and it screams. We're living in the moment when the universe is finally old enough for the first wave of deaths. We're witnessing the end of objects that were born before the first star ever ignited. If this sounds like science fiction, I don't blame you, but this paper was published in Physical Review Letters, one of the most respected peer-reviewed journals in physics. The statistical confidence is 5 sigma, that's the gold standard. It means the chance this is random noise is 1 in 35 million, essentially zero. The skeptics will push back. They'll say maybe it was a cosmic ray shower, maybe a magnetic field we don't understand, maybe detector error, and that's good, that's science. We need to test this. We need independent confirmation. But right now, the dark charge primordial black hole model fits the data better than any other explanation on the table. And here's what keeps me up at night. If we're right, if these black holes are everywhere, quietly evaporating, then the universe is far more active than we ever imagined. It's not a cold, static graveyard. It's dynamic, violent, full of invisible objects that have been waiting since the dawn of time to announce themselves. And we're only just now learning how to listen. So what do you think? Are we witnessing the death of ancient black holes from the Big Bang? Or is there another explanation nobody's thought of yet? Drop your theory in the comments. Some of the smartest insights I've ever read came from this community, and if this video bent your brain even a little, smash that like button. It helps more people find stories like this. Subscribe if you want to be here when the next impossible particle shows up. Because it will, and when it does, we'll be ready. If you really want to support this kind of deep investigative content, consider dropping a super thanks. It directly funds the research, the time, the late nights digging through papers so we can bring you the cutting edge of science before it hits the mainstream. Every bit helps. We just saw a black hole explode. And in doing so, it may have unlocked the dark matter mystery, revealed the quantum nature of spacetime, and given us a direct window into the first second of creation. One particle changed everything. The universe is stranger than we ever imagined, and we're just getting started.